Welcome to On the Metal, Tales from the Hardware Software Interface. I'm Bryan Cantrill. With me, as always, is Jess Frazelle. Hey, Jess.
Hey, Bryan.
And joining us is our boss, Steve Tuck. Hey, Steve.
Present.
All right, Jess, you want to introduce who we've got in the virtual garage today?
Yeah, so remotely, which is a fun one, we have John Graham-Cumming, who wrote the Geek Atlas. I was just looking at that this morning. And the Make book that I also have, and also works at Cloudflare as a CTO.
All right. John, welcome.
Thank you very much. It's very nice to be able to talk to you from far away.
Yeah, and this is a conversation we've really been looking forward to having for a long time, because when you dial up computer history, which we've been known to do in this podcast, you turn the dial all the way back. Do you want to talk about how you got into Babbage and his work with Lovelace and so on?
Yeah, I mean, I think I probably knew about it at university because it was mentioned as like, oh, by the way, there was this other thing, and maybe it was a computer, Charles Babbage. And then what really happened was, right at the time when I was at university in the UK, the Science Museum in London started building one of Babbage's machines, this thing called the Difference Engine, which is really a very big specialized calculator. It's not a computer, and they started actually taking his plans and building it. And I, because of where I lived when I was at college and when my parents were, I used to have to travel through London. And so I would literally go through London and sneak out of the tube, go into the Science Museum, look at this thing being built, and then slowly it would get bigger and bigger and bigger because they built it in public.
Oh, wow.
Which is really, really cool. And so I kind of knew about it. And I remember at one point, I had this really strong memory of taking my girlfriend, who was also a mathematician, to see this thing. And then the two of us go, okay, the method of difference is let's sit down. And we sat down on this. There's a little patch of grass outside the Science Museum. It's not a very grassy area. Sitting down on this patch of grass on a sunny day in London. That's why I remember it.
Right. Very distinctive.
and sitting the two of us with a piece of paper working out, okay, how does this thing work? How does the method of differences work? So that was probably really when I got excited about Babbage. And then, subsequently realized that the difference engine, as cool as it was, isn't actually programmable, and that was a bit sad.
And did you already know at that point that you were interested in computing? I mean, had you grown up in computing at that point?
Yeah, so I was doing mathematics and computation, as Oxford called it, because Oxford was very theoretical. It was all about the theory of computation, none of this messing around with real computers. But I had messed around with computers for a long time because, well, if you sort of go backwards, you have to work backwards. I was obviously a child of the 80s, 8-bit revolution in the UK. I had a thing called the BBC Micro, which was this really cool computer with 48K of RAM.
I feel whenever the BBC Micro is mentioned on the podcast, it's been mentioned a couple of times, I feel that all of our English listeners play God Save the Queen in the background. I feel that there tears in the eyes.
There are two groups, right? So in the UK at that time, there was the Sinclair group, right? The ZX81, the ZX Spectrum, and then there were the BBC Micro people. And so, we were sort of two camps. And the Sinclair machines were slightly cheaper.
Okay, I've got so many follow-up questions. Is this a class divide? Is it geographical? What divides these two clans?
I mean, there was definitely a price difference. The Sinclair machines were much, much cheaper. So I think they were much, much more widespread. Whereas the BBC machines were in schools, so people got at them at school. And I ended up with a BBC machine because my parents, in their wisdom, had said, well, they had two boys, and they're like, we'll let these two boys do the things they seemed really interested in. And my brother had years and years of piano lessons and played the piano really well. And I said, I want to have a computer. And they said, well, we probably spent that much money on piano lessons, so we'll buy you this machine, which I still have, which I treasure. It's
wow.
That's cool.
Wow.
And so it's like, it was a big, big deal. And it was very funny, actually. I switched it on a few years ago, and immediately the power supply blew up, so I had to replace the power supply. And I looked at the back of it, and it has the wattage of the machine, which was about the wattage of a light bulb. And I remember thinking,
really?
I knew that my parents didn't have loads of money to burn, and they'd spent a lot of money on this machine. And I had this incredible feeling like, oh my God, I can't run up their electricity bill with this machine. So I used to switch it on and then go and switch a light off somewhere in their house to be like net zero. I actually don't think my parents had that little money, but it was more like I had this thing where I was like, I gotta.
If the draw is like 60 watts, this is like not even observable on the power bill, I assume.
I guess, but I felt as I was a child, right? I was just like, I've got to do my bit. So
what a conscientious child!
It's really cute.
Meanwhile, like my children,
I'll take one of those.
I'll take one of those too. I can't get my kids to be like, could you just get off the mobile network and onto the Wi-Fi so you don't bankrupt the household watching YouTube?
It was a different time.
It was a different time. Children were so mindful of the power bill.
But actually, if you to continue answering your question, if you go really right back in time, at some point when I was about, I think 7, I was very bright, and my parents were like, "What the hell do we do with this bright kid?" And they found, and of course it's pre-internet, right? This is like in the 70s. They found this association, which was, for desperate parents of intelligent children, basically. And they were like, what do we do with him? And they did this thing at Cambridge University in the summer where you could basically take your kids and dump them off and, let your kids run wild. And so I went to that a couple of times, and I actually hated it because some of the kids were so snotty.
Right.
But there was one person I went up to, and obviously this person was in either the mathematics or computer science department at Cambridge. And I said, explain to me how a computer works. I want to know. You imagine I'm like 7 years old. And what I remember of that is the person getting out a pad of paper and starting to draw this strip on it and little boxes on it and basically described a Turing machine. And I have at home my own little Turing things I've tried to do in strips of paper and come up with this computer thing. So I think I was infected with computer stuff pretty early on. And my mother would say, even as a baby, I was fascinated by things like, how does a clock work? I would stare at clocks. Like, how does that work? So, I don't know, something happened. Probably in the womb, maybe.
So where is the 8-year-old that explained the Turing machine? Where did he end up?
Oh, no. This was a professor.
Professor. Excuse me. I'm sorry.
It was an adult. I mean, whether he was 21 or 40, I have no idea, right? As a child, somebody sat and explained this to me. I was like, whoa, this is amazing. And then, of course, later on, I go to do computer science. I was like, wait a minute, that's a Turing, this guy Turing. And now I hear about all this stuff for real and some of the theories. So I was into computers from an early age. I was kind of nerdy.
And you were obviously writing your own programs on the BBC Micro?
Yes, obviously. So I think I started out just playing with the machine, trying to understand it. And then I bought this book that was called The Advanced User's Guide, it had a lot of stuff about how the operating system, sort of the BIOS for this thing worked, and a lot of the guts of it. And I was very interested in that. So I really learned assembly language and then started doing assembly language stuff on the machine. And at the same time, I was programming another 8-bit machine, which was made by Sharp, I think called the MZ80K, and then some other Z80-based machines.
So the MZ, to give 80K, you the 80K. Interesting.
Yeah, it's a bit like a Commodore PET as an integrated CRT and a tape player. And unusually, it had a keyboard where you could actually type every character that was in the character set. It was really weird because it had it didn't have ASCII. It had its own thing with all sorts of crazy symbols and stuff. and you could type everything. So anyway, I was really into assembly language programming, and then basically to make my programs faster or to access bits of the operating system, and built various things. And me with another boy at school, at high school, we wrote programs. So we wrote a statistical analysis package. We wrote a thing for timetabling. And then basically around this time there, we had a 800 kilobit per second, I think, local area network at school. And we disassembled the operating system and figured out how to make it work. And funny thing was, we disassembled how the operating system worked so we could get access to the network. And then we implemented our own packet send and receive routines, implemented our own stateful protocol on top of it so we could reliably send stuff, built a network management package, all of this in assembly language.
Well, and all of this very early for networking, for local area networking, right?
Yeah, exactly. There was this company in the UK called Research Machines that sold computers to schools, and they were first going on. And the school I was at, the high school I was at, called an upper school in the UK, the head teacher died very suddenly of a brain hemorrhage. Now, a
Oh
lot
my
of
gosh.
money was raised, and the money was spent on this new thing, which was a computer room.
Ooh, cool.
And in the computer room, they had a network of these Z80-based machines. And myself and another boy, we hacked them, basically.
What was the substrate? Because this is going to be too early for Ethernet, right?
Well, it was this thing called ZNet, which was their own.
ZNet.
Yeah, I mean they made their own network stuff, really. So the central machine, so the machines were running CPM,
Right.
and then there's the central machine that was running NPM, which had 8-inch disks, and then they had this networking thing. I think it was called what was it called? It had a funny name, but it was 10 base 2, basically coax.
It was 10 base 2. Okay.
Okay, so it was coax. Chain, that's what they called it. They called it chain, and 800 kilobits per second. The MAC address was an 8-bit address
Okay.
on a dip switch in the machine. So you just went and plugged it in.
Interesting experiment.
I mean, it was a whole thing, but it worked.
Wow.
The best thing is that myself and Peter, who was the other boy who really got into this kind of stuff, we used to sit physically closest to the file server machine as you followed the network, because it was coax, you could actually remove the connector at the end, terminate it with a BNC terminator, turning the network into a network with the file server and 2 machines, and then up the performance because you just cut off the rest of the network.
That's dope.
You just close the door to the rest of the network. Wow, things get a lot faster. That's great.
Yeah, so if you did a file transfer and the other kids in the class were getting on your nerves, you just pop the network off, terminate it, do your file transfer, and put it back again. And you can hear the other kids complaining, why isn't the computer working? Well, I don't know. Maybe it's this BNC terminator we put on the end of the thing.
That's great. Well, again, that is very, I feel, early for networking, especially in a school. So what year is it at this point?
I mean, it's 1984, I think.
That is very early to be networking in a school.
It was fascinating because we got access to this thing. And then the really nice thing is that I wrote to the company and basically said, by the way, we've reverse engineered the entire operating system. We're doing all this stuff. Will you give us the documentation? Because we're like, we'd like to actually have the real documentation. And somebody from the organization wrote back to us and said, essentially, and I actually published the letter on my blog, but they essentially said, don't tell anybody, but here's all the documentation for this thing.
And did you reveal that you were 14 or whatever you were? I mean, did they know?
Yeah.
They knew that this was a bunch of kids that had.
It was really, really, really encouraging actually, because we were just hacking this stuff on our own. We didn't really have, we didn't know what we were doing. We were just reverse engineering everything. And when we were like, we did things like we wrote a paint program, and we were sort of sitting there going, oh, how do we do like fill an area with a color, and writing flood fill and all this kind of stuff. So,
and this is for these machines.
Yeah, for these machines, for this research machines 480Z, it was called. So I actually have the letter here. It's like, thanks for the letter. Don't tell anybody, but here's the documentation.
But I'm just amazed that you're writing that it had the graphics horsepower to do a paint program in 1984.
It did. It had. It was a very simple graphics program. I'm trying to think. I think it was I think if you, in black and white mode, it was like 640 by 192, I think. And I think in like the color mode, it was like 320 I think it was 16K of video memory.
Still though, you think of like, this is before the Mac.
It's about the time, right?
Right, yeah. That must have felt
impressive.
That's very impressive to be. It must have felt like you were really, did you feel like you were on the cutting edge of computing? Because you, certainly from a personal computing perspective, you more or less were in 1984.
No, I don't think we had any perspective. I think we just had these machines, right? So I had the Sharp machine, I had the BBC Micro at home, and I had these networked machines at school. And I just remember more than anything feeling like we could do whatever we wanted with these machines, because we knew every memory location, what it did, like the memory mapped IO. We completely disassembled the operating system. I think Peter wrote the disassembler as well. So a lot of stuff we wrote, right? Because we're like, it's getting boring just looking at the Z80 opcodes. So let's write a disassembler, and then we were bootstrapping from whatever we had, and it was fascinating. I still have a lot of the code, And
Wow.
we wrote this network management package for this network entirely in assembler. So that you could like send a message to machines. So we wrote a chat program, all this kind of stuff.
I mean, I feel like that was kind of pro grade. It was pro grade work at the time. That's what I mean. Effectively, there were a bunch of companies that were endeavoring to do that same thing at that same time.
I think you're right. I think it's about the time where stuff was really taking off, and we probably, I was a teenager. I probably could have gone and got a job somewhere else. But
Yeah, right. Exactly. You could have like dropped out of school entirely. Was it tempting at all to be like, I know everything there is to know about computing, so I'm going to set my because I'm actually impressed that you studied computing or computation at university.
Well, so here's a really interesting thing, which is that I was doing this, Peter was doing it, and there were really the two of us in the whole school who were really deeply into it. And I think that outside of that little world, it was not obvious in 1984, 1985 that this computing thing was a good career, particularly not in the UK.
Yeah, interesting.
It was kind of a hobby thing, and you were messing around and wasting your time, and you should go and get a proper job afterwards.
Yep.
And I actually really, really seriously considered being a lawyer.
Yeah.
Because I thought, maybe this computer, what is this? This is I'm gonna mess around with this. I don't know what my job is going to be, and in particular, the sorts of jobs you're going to get are like technicians,
right?
And it was really looked down on. It was like there was no distinction between software engineer, which the term didn't even seem to exist, at least from my perspective, and someone who installs a phone in your home.
That's a very important point, and you do actually forget that because I grew up slightly later, but in the 80s.
Yeah.
And actually, my father, who'd written software when he was at university, didn't for a moment contemplate doing it for a career. He became a physician because it was viewed so pejoratively at some level. I mean, it was viewed as something that you were like messing around with and having fun with, but not something that, I definitely remember my mother vividly telling me you can't play on the computer forever,
Yeah, absolutely. I mean, I think my parents were, I was obsessed with the thing. During the summer, I stayed inside the house basically the entire summer in front of a machine. This was in front of the Sharp machine, writing a bunch of stuff. And I wore through the bottom of the trousers I was wearing just from shifting in the seat. So it's like, it was a little bit obsessive.
At this point, are your parents thinking, we really need to get John a piano? Are they are they thinking that we have overshot the mark on?
No, I don't think so, actually. I think that they were worried about me not going outside and socializing more than they were worried about the computer. I think it was just, why is he spending so much time inside? What is he doing? On the other hand, I seem to be enjoying it and I wasn't causing any trouble. So.
And you were very mindful of the power bill. I mean, I just
turning off lights, sitting in a dark.
Exactly.
Can't imagine such a considerate child. And so then you head off to university, and it's not too much longer thereafter that you're on the sunny lawn in London trying to figure out the difference engine.
Exactly. Well, I took a year out actually because I had I jumped a year at school, so I felt like I was a bit young to go to college. So I took a year out, and I went and did a bunch of electronics stuff. I went to a local technical college and just did electronics. So I was kind of interested in electronics to kind of learn about how things really work. But yes, then I got to Oxford, and I'm going back and forwards to where my parents lived, and yes, Babbage comes along. Although I would tell you one funny thing, which is that years after all of this, within the last few years, I read a school report of Alan Turing, and in it, the schoolmaster is saying, you really ought to do better at all these other subjects other than just, science and mathematics, because if you don't, you will grow up to be a mere technician.
Oh, geez.
Yeah.
Which happened, really. I mean, he didn't do much, really, Alan Turing, just a technician.
He's really just a technician. Yeah.
Yeah.
And it is interesting. And, I've got mixed feelings about the fact that now there are, most college campuses in the U.S., the introductory computer science course is the most popular course on campus, having surpassed the introductory bio classes. It's amazing.
Really?
Yeah, Jess is giving me a crazy look. No, that's true.
Where did you read this? I didn't know that.
This is. I mean, if you talk to any university,
that's crazy.
Yeah, no, that's
crazy. It was not popular when even I went to school.
No, this is. Well, it is. It's an economic thing as much as it is anything else.
That's right. That's right. There's money in it, right?
There's money in it.
Oh, that's true. Like nursing was huge.
Right.
my year.
And now, I mean, you can imagine if you're a parent of an 18-year-old who's concerned about the economic viability of that 18-year-old, you're probably telling him to take the computer science class.
That kind of ruins it a little bit, to be honest.
Well, that's the question, right? I mean, it's like there was something pure when nobody was pursuing it for economic reasons.
There was like 12 people in my class.
Right.
12 people.
It was so small. And then I was the favorite. I mean,
Sorry, did anyone ask? Just want to make sure.
Sorry.
You know, I have in doing this, I've heard so many stories of Jess and her adventures in math class. So Jessie should know is the person who sets up like all of the trapper keepers around her math exam to make sure that you cannot see anything that she's working on.
I want to be the favorite, and I want to get the 100%. Like I don't want people to cheat off of me.
I know. I feel like
it's reasonable.
I feel like I was in your math classes with you. It's such, your descriptions of math class are so vivid, but it does feel like there is something when you are drawn to it, kind of despite societal pressures to do something else. The people that end up being there are the ones who are really deeply, deeply drawn to it.
Yeah. I mean, I think the thing I really felt was as much as Peter and I were working on stuff together, there was an intense amount of competition. And I know I was incredibly annoyed when he did something clever, like because I really wanted just to master the whole machine and prove how brilliant I was.
So dare we ask, where is Peter today?
Yeah, I was going to ask.
I have seen him, and he does something that's designing something for the British government and can't tell you about it. So I don't know what it is exactly, but it's some electronic things.
Is this an elaborate multi-decade plan to get even with you? Maybe he's like, I'm going to show it to Graham-Cumming.
And again, a satellite is going to suddenly shoot me. I don't know. It's been quite a few years. He went to Cambridge. I went to Oxford, and in slightly different directions.
So then you're looking at the difference engine, which I think both the difference engine and the analytical engine are so fascinating because they are mechanical, not electronic. And a couple of questions for you on that. And for those folks who haven't seen it, we'll obviously link to it in the show notes. I mean, you gave a great TED Talk on the reconstruction of this. I guess before it was really reconstructed. I mean, as you were showing the simulation. So in particular, you had some programs that Babbage had written for it. And I guess I didn't realize that he'd actually written programs for the thing that he had not built.
Yeah, I mean, I think so. If you look at all of the stuff that Babbage left behind about what's called the Analytical Engine, which is his computer, which is the thing that he worked on with Lovelace, there was simultaneously designing the machine and thinking about what the programming language would be like, what the instruction set would be, basically. He basically came to this idea that the difference engine was limited in what it could do because it was fixed in terms of its program in a way. And also it couldn't really do much with its output, and it couldn't sort of fundamentally take its output and feed it back in and do something with it. And so he realized that there was functions he couldn't compute. And the thing is about Babbage is he was completely obsessed with mathematics. This is all about computing mathematical functions. And so he realized he could make this more flexible machine, programmable with punch cards, and why punch cards? Because they were widely used for looms, for weaving. That was a technology that was available. And he's kind of making the instruction set and thinking about what the machine will look like and how to optimize the machine at the same time. So there are in the Science Museum stacks of cards all threaded together with programs on them, fairly simple. This is the sequence of things you would do to calculate some function. The problem was, first of all, I think Charles Babbage was, like many nerds, a little bit difficult to deal with. He also realized, like, it's the classic thing, right? He makes the difference, or he designs the difference engine, and then he just abandons it. Because it's like, I can make an even better one. So eventually the British government said to him, we've spent as much as a battleship on this thing, and you haven't actually built anything. And he's like, yeah, but the next version is going to be the coolest because it's going to have, there's such and such features. So eventually his funding got cut off. He was constantly optimizing the machine, adding instructions, making it faster. And he realized things like, well, I could essentially have instruction pipelining and data pipelining. Like, well, while the CPU bit is doing an instruction, I could be moving the next data from the store, as it's called. He's just a classic nerd. And then in his notes, he's like, maybe I need 100 memory locations. maybe I need 1,000 memory locations. You remember this thing's physical, right? So it's ending up the size of a locomotive.
Well, it's physical and it's also unbuilt. This is the thing that is so amazing to me, is that he is doing all of these optimizations on a system that is not built at all. I mean, I think that, this is, I think that the thing that it sticks out the most to me about Babbage is like, how are you, most of us need to actually like mess around with something in front of us to really wrap our brains around the system. And he is able to truly, we talk about keeping the system in your head. He truly kept the system in his head. I mean, he did. Yeah. And Lovelace too, clearly from their interaction, she understood how it worked, was able to imagine the sequence of events. I mean, what's funny about him is he's thinking both of it logically, right? And also physically. And at some point in his evolution, he realizes that he needs a hardware description language because it's complicated to describe the physical thing. Right.
When really what you want to do is describe what the physical thing does. And so he invents a hardware description language.
Like mechanical Verilog? What is this?
Yes, basically. So he's like, so for example, he uses his hardware description language to describe a clock, how a clock operates. And he said, if this component turns around 60 times, this component then moves one step, right? So it's like abstract without it being how that's actually implemented.
Wow.
And so he did that. And of course, classic nerd, he then along the way is like, I'm going to change my hardware description language. So the problem with building the machine is it's a moving target.
Right.
So there's plans, there's pages and pages of hardware description language. There's also, funnily enough, in some of the best developed plans, there are whole sections that are left unfilled in. There's like a blank bit. And looking at his documentation and what he wrote down, because we have his lab notebooks, basically thousands and thousands of pages. He's basically saying, that bit's obvious. It's obvious how we'll do that bit, which might be the card reader or something like that. The other thing he did is really interesting is microcode. So he basically, the punch cards describe an operation like addition. Then you've got to actually cause a physical thing to do addition by moving numbers around and carry operations and stuff like that. So there, he's like, okay, well, essentially he microcodes that. And the way he does that is it's on the sort of physical barrels, like in a barrel organ. They have a load of pins sticking out of them. So you have one of those for each instruction, which can then make the machine operate.
And that's the microcode effectively.
That's the microcode effectively. And
wow.
Then you have the machine. But it's a very similar architecture to one you would recognize. It's got a central CPU. It's got a bunch of memory. Right. It's got ingress and a bus, which is, especially the memory bus. So it's quite recognizable. I think that's what's so tempting about trying to build it is that anyone who's actually looked inside a computer will go, oh yeah, I can see where the CPU is. I can see all these, analogies and all of the optimizations he was making is unbelievable.
A stupid question. Was it buildable at the time? Could you have machined it, or was it relying?
Yes.
Okay, it was actually buildable.
So that's really the cool thing, actually, right? Which is that, here's the other crazy thing about Babbage. The manufacturing techniques were, everything was hand-built. And so, for example, at the time, if you got nuts and bolts, you had to go back to the same nut and bolt manufacturer because there was no standardized threads. So Babbage, before actually embarking on building even the difference engine stuff, he went on a tour of England, going to visit people who did manufacturing to understanding the state of the art in manufacturing. And he eventually teamed up with someone in London who had an apprentice, and that apprentice was the person who ultimately would standardize screw and nut, bolt threads.
That's crazy.
Like, you mean like that? That's what as a contribution to humanity. Like this is the standard. Yeah. Wow. Okay.
He's clearly good at hiring.
Yeah, I mean, he is very good at hiring. Yes.
He was very wealthy, right? That helped as well, right?
Yes.
But what's clear is he had to bootstrap the whole thing. He's like, I don't have any manufacturing techniques. Okay, well, I'll figure that out. But what's important is when the Science Museum built the difference engine, they did it using materials and machined in such a way that is with the tolerances that were available.
Oh, wow.
At the time. So they know that the machine does what it should do and would have been reliable. And so I think we have a good sense that the analytical engine would also be reliable and actually operate. Another really fascinating story about this is if you think about in electronic computers, when you have a signal going between components, you quite often have to make sure the signal is amplified in such a way that it's either a 1 or a 0 clearly, because you get some fan out cost, right, to the electrically. The equivalent in his machine is that he has the numbers that are stored in the memory are stored on a wheel with a cog on it, with a gear on it, 0 to 9. And obviously, they might not move perfectly into position when you do additional something. So he has this little triangular thing that shoves in to the gear and actually pushes it into position, into whatever the nearest number is. So it's exactly an analogy of an amplifier, where you're going, say, between logic gates, where you're keeping the signal at the right level. It's fascinating to see these analogies between the what happens in electronics and what happens in hardware. But we kind of shouldn't be surprised because, many, many, many years later, Church and Turing come along and tell us, well, all this stuff is equivalent, right? It doesn't matter how you do it.
Interesting.
So was this ever built before the Science Museum picked it up?
The difference engine was not.
No.
Never built.
Never built.
No one picked it up.
So other people saw that Babbage talked a lot about. He built some little example pieces, components, and then other people saw them and said, we can build a difference engine too. And so there were other people who built smaller models, not quite the same scale as what Babbage was doing, but then Babbage's machine eventually got built by the Science Museum, and you can go see it. And then there was a copy in the Computer History Museum until it was taken back by its billionaire owner.
Who's the billionaire owner?
Yeah, that's shitty. Who does that?
It's dark.
So they can throw it off the back of their yacht?
So Nathan Myhrvold, CTO of Microsoft, he paid two things. He asked the Science Museum to build one so he could have his own difference engine. And he sweetened the deal by giving the Science Museum enough money to build the bit of the difference engine that they had never got round to building, which was the printer. And so the reason Babbage got into this whole difference engine thing is you have to go back. You're 1800s. Britain is this massive naval power. It needs really accurate information for navigation. And, you may have heard about the longitude prize, which was to get this really accurate clock. But what you also need books of tables of numbers, like log tables, sine, cosine, all that kind of stuff, so you can do calculations. And the problem was these things were created at the time by people who were called computers.
Right, yeah.
Sat and calculated these things, and they printed these books. And Babbage famously said to a friend, I think at college, I wish this damn thing could be all computed by steam, because that would be accurate, right? That's what set him off in this whole path. And the reason he was thinking that is he and a friend from college had a fun time going through books of, say, log tables or sine tables and looking for errors, which sounds like a great evening thing to do. But there were lots of errors, and finding errors was a valuable thing. And so he was like, if I could just make a machine that did the calculation accurately, then not only that, but removed any problem of transcription, it will actually print out the results automatically. And so it would actually print out on paper and also print out in such a way that it was possible then to reproduce that mechanically in a book. So it would actually make you a lead sheet. So you could just take it straight. So you'd be absolutely certain your book of log tables was accurate. So he did the whole thing. And so, this was actually built, and it does actually work as well as prints. And it even does justification as well, the printer, all mechanically.
Wow.
So that's cool.
It is justification.
That's such a detail.
It's such a detail for something that exists only in your head. I mean, it's remarkable to me.
Yeah, but he was trying to make this real thing that would be really valuable, and he was thinking through all of the issues. Like, what if it's off by a little bit? What if, how am I going to print it? How do I remove a transcription error? What do I do if something goes wrong? And so...
Amazing. All right, we got to take a quick break. We're going to be back in just a moment with more John Graham-Cumming.
On the Metal is brought to you by the Oxide Computer Company. Well, thought we had a bit of time to deal with this, but it sounds like the listeners are pretty restless.
Uh-oh, is this about the ads?
Yes.
Oh, no.
The inbox is full.
Oh, boy.
They also have begun recording their own ads and sending them to us, requesting mercy from the repetitive ads that we've been subjecting them to.
Wait a minute. They're in such pain over the ads that they're sending us ads for Oxide?
Yeah. I picked one out. Have a listen. This is from listener Paul Guaz.
I'm getting really, really, really tired of listening to the same Oxide.computer ads every week, talking about how the Oxide Computer Company is going to make your on-premises infrastructure faster, more efficient, more secure, and just all around less painful. So much so, in fact, that I wrote and recorded this ad. Head on over to oxide.computer to learn more and join their mailing list.
I think we should just do what Paul said.
Yeah, let's just follow his instructions.
So let's get back to the show. And we're back. All right, we're talking about steam-powered computing, literal steam, and Babbage working on his printer. So when they put these things together, and we'll get to Nathan Myhrvold in a second, and him taking back
it's cruel.
That's cruel, and we're gonna call him out for it. But were there any? Surely there were bugs somewhere in this. Surely there were things that didn't work correctly, or did Babbage really? Did he get this whole thing nailed?
Well, I think he did get it nailed. So what we know is that when they built the difference engine in the Science Museum, there was a problem which they identified when they were looking at the plans. And the problem was that something was inverted. And the speculation is that Babbage may well have actually deliberately introduced the error so that someone, if they were copying it, would not be able to get a working machine.
Wow. Okay. All right. I mean, that is a testament to like your code is so bug-free that when I find a bug in it, I legitimately think that it was introduced deliberately.
Right, exactly. So now, having said that, when they got onto the analytical engine, and there's these letters back and forth between Lovelace and Babbage, this is where you get into the program is actually buggy, and that's really where Lovelace and Babbage going back and forwards over this program to calculate a sequence of numbers, and they're like, wait a minute, this doesn't work, and they're debugging on paper this thing for a machine that doesn't exist.
Wow.
That's so cool.
That's amazing. And are they doing this via correspondence?
So yes, actually. So obviously they met a few times in person, but a lot of it is done by literally by letter.
That's so slow.
Wow.
That's so slow. That development cycle, just think, that is like the world's slowest.
Exactly. Yeah, I mean, people complain about the speed of deploying to production. Why don't you try debugging via exchanging letter?
Instead of waiting to compile, you're waiting for the postman.
Oh my gosh.
Yeah, for a machine that you don't have.
Yes, and that has never been built.
Your computer yet.
Wow.
So, what I would really like to, I sort of get how Babbage got into this, right? He sees this problem of these tables and he thinks, yes, this could be mechanized, and he keeps going and going and going, and he's just building and building on it. But what was Lovelace's deal? She was like a teenager. She walks in, sees a demonstration piece of Babbage's thing. Babbage explains it to her, and she completely gets it. What was her deal? She'd never seen a computer. She's like, great, I'll program that then. Where did she come from? Because I think that's the thing that's fascinating. She obviously had a mathematical background. And actually, if you read Babbage's correspondence, she's really the only person who groks it.
Interesting.
Well, okay.
Interesting. I mean, because I was going to ask, how is this seen more broadly by even others that are mathematically inclined or mathematicians? How do they view all of this work at the time?
I think the big thing is they view it as he hasn't actually built the machine.
Right.
And he keeps asking for more money. And when are we going to get one of these things? And I think that's the big thing. People understood what he was trying to do, particularly around the difference engine, because that had a very, a real purpose that everybody understood. It's not well understood, I think, widely what the analytical engine was about, because that was far out. It was like, we're going to make this programmable thing and run arbitrary programs on it.
Well, and it's kind of the curse of the cross-disciplinarian as well, right? Because it's kind of straddling mathematics and mechanical engineering in a way that is probably at some level foreign to both disciplines, I would imagine.
Yes.
Is that a fair inference?
I think that's not a bad point, actually, which is because it's very, he's going from a very, very theoretical world, and then he's we've got this physical machine, and then people are wondering, what is this guy on about?
Right.
And also, you talk about Babbage is also dabbling in all sorts of other areas, like, we could probably, one of his famous things is we could probably figure out what the ancient climate looked at by cutting down trees and looking at the rings, like how far apart they are. He's code breaking things for the British government. It's like all sorts of stuff he's doing. His biography is fascinating. And at the same time, he's arguing with the establishment in Britain about various things. He's basically calling other scientists a bunch of idiots and stuff like that. And then he was offered a knighthood. He was going to be Sir Charles Babbage, but the knighthood he was being offered was not the one he thought was the right one. So he turned it down.
as one
Basically,
does.
he's like building this machine and dissing everybody else and the whole stuff.
It's so good.
It's not ideal situation. The only thing that's really, really tragic, of course, is that Ada Lovelace died very young.
Oh, wow.
Yeah, I was going to ask where she
had
went.
cervical cancer and died in her 30s.
Oh, my
that's really
gosh.
sad.
Oh, wow. I did not realize
So
that.
Babbage, like, nobody understands him. This 16-year-old girl turns up and says, yeah, I get this. I'll program it with you. They go with this long correspondence.
And then dies young. Oh,
and then
my
she
gosh.
dies. And then he lives for years afterwards, having lost the only collaborator he gets. And there's this one description, because he doesn't describe this himself, but he went to the US at some point trying to raise money because, here you go again, this is such a old but modern thing. He said, no one in Britain understands me, but Americans will understand because they'll think, how can I make money out of this?
So Charles Babbage heads to Sand Hill Road.
Yeah, exactly. He basically goes to the US to try. And in fact, what he does is he decides to make a machine that will play tic-tac-toe, which will show people in the US, therefore they'll give him a load of money and he'll go build his machines. But while he's in the US, somebody asked him about
So good.
I mean, you just gotta
gotta go to-
pause. I know you gotta. Well, I think
Gotta
so
go to the
good.
U.S. because
I
they'll pay me
actually-
money for tic-tac-toe.
I envisioned him on Sand Hill
Oh, so
Road
do
when
I.
you said
Oh.
that, and then I just couldn't get over
Oh,
it.
and then you envision all these VCs, these 19th century
Turning it
VCs,
down.
and it's like, we'll be cheering for you from the sidelines, and make us. Yeah.
Anyway, so he goes there, but somebody recounts. I can't remember what it is, but this is written up. Actually, somebody wrote a letter about it, that they had said something to Babbage about Ada Lovelace, and she had died not long before, and that there's just description of him just falling apart in despair that she was gone, and that this was his intellectual equal in this process, and he was probably in his 70s at this point, and she was in her 30s, but they got it. They understood how to make this what this future was. And in a funny way, she understood it more than he did, because he very much was obsessed with this idea of these mathematical equations. He built all this mathematics in it. And she's there, and she says it in one of the papers, like, hey, but we could represent pretty much anything by numbers, like music or symbols or letters, and we could compute all sorts of other stuff.
Yeah.
And it's like,
And you called that the
that's
Lovelace leap, I believe.
I call it that because everyone talks about her being the first programmer, which is fine. But, honestly, between her and Babbage, they were both coding.
Right. Yeah, exactly.
But this thing where it's like, hey, Babbage, you're building this machine, but by the way, we could do text processing and music, and it could compose music and all this kind of stuff. It's like, that is a huge leap.
That is a huge leap.
That's cool.
That is,
Right?
no, it really is a huge leap. And to do that again on a machine that's not built.
Yeah.
I know, exactly. So
It is a huge leap. And so when do they get kind of fully appreciated for their, at what point does kind of society realize that they were truly, ahead of their time by 100 years almost?
Well, I think the thing that's interesting is they were definitely ahead of their time, but Babbage and Lovelace are kind of like the uncle and aunt of the rest of computing, because it's a complete dead end, right? They do this stuff. She dies, he dies. His son carries on a little bit of the work, but it really goes nowhere. And it kind of stops, like end of the 19th century. And then middle of the 20th century, or in the 30s maybe, computing reappears again, but now electronically or electromechanically at least.
Right.
And so it's like two separate tracks where there's not really a direct Babbage to modern computing connection.
So I was going to ask, so with the kind of the census machines of the late 19th century, how did they even view themselves as inheriting any of that legacy, or did they?
I don't think so.
Interesting.
I don't think so.
Totally
I think
separate
this was
track.
just,
Yeah.
other mechanical things that were there, and clearly people were aware. The folks who worked on the Harvard Mark I, they say, there was this other attempt in the 19th century, and Turing, in one of his papers, he talks about Ada Lovelace and was aware of, because Ada Lovelace was wondering whether this machine could think.
Wow. That is so ahead of its time.
All right, Ada Lovelace, like how much of the future are we going to envision here? This is like, wow, interesting.
I know. I do wonder, if she hadn't died, would she have kicked, Babbage and be like, can you just build the damn thing? Like, I've got stuff I've got to write.
Wow.
I've got programs to write. So
That's an interesting thought.
Yeah.
If Lovelace had lived, would
But
she
one
have?
thing I think is really interesting is right about this time, right at the same time as Babbage is here with his mechanical computer, Michael Faraday is in London with electromagnetism, and he's making transformers and relays and solenoids and all this kind of stuff. And it's quite clear that Babbage was obsessed with doing it all mechanically, and this electromechanical thing was way too new and wasn't reliable. And we knew how to handle gears and all this kind of stuff. And so you almost, I've actually wondered sometimes, is suppose Babbage has succeeded, would he have actually set everything back? Because we would have perfected mechanical computing. We would have got it really good, and we had all these mechanical computers. Faraday be on the side there going, you could do this about 1,000 times faster with electricity, right? And we're like, no, that technology's too new. It's unreliable. So.
Oh yeah. That could have totally set a different time in motion.
Oh, you can just imagine a lot. Well, you can also then imagine. I mean, I think you can also imagine the machine gets built and people realize that this could be done much faster with relays and so on, and then computing gets jump started 60 years earlier.
Yeah, maybe. Who knows? Anyway, Babbage and Lovelace were really smart, and definitely Babbage was. If Lovelace can be called the first programmer, then I really think Babbage is the first computer nerd.
For sure.
Well, it's all right. So here's another kind of question in terms of, because in terms of how the history of computing actually gets written, even the census machines and so on, and the kind of accounting machines of the early 20th century don't actually get us over the hump. It ultimately takes the existential threat of a world war to actually get humanity over the hump with respect to computing. Or maybe did it?
Maybe that was just happened, right? That in the 30s, Turing is doing some theoretical work, Church is there, and some stuff is happening, and then yes, the war is there, but I don't know. But maybe the war gave us some bunch of money, but feels like the time was ripe.
Interesting. Okay.
So Shannon is there thinking about, we could do all this logic we want to do. We could do it with electronics. I don't know. I'm not sure the war is actually essential. I mean, the war certainly, a lot of money got spent on computing.
Well, it certainly focused the mind on the problems at hand. Yeah. But interesting. So all of these things were kind of building up, and it was. Do you think that there was a bit of inevitability to it then at that point?
I do think it was kind of inevitable, yes, because if you look at the way people were thinking about things, and then there was this process in mathematics where there was this idea that maybe we could mechanize a lot of stuff that was happening in mathematics before there were machines. So I think even from the theoretical side of things, the mathematicians were thinking about these things, which is how Turing gets to it, actually. He's trying to solve a problem in mathematics. He's not trying to invent a computer. But along the way, he's like, so in order to mechanize this thing, I need some sort of machine. And then he describes this universal, what he calls a machine, which is what we can now call a Turing machine.
Was this a budding kind of theory of computation then in math? What's the outgrowth of math that Turing is coming from?
Well, so there's this thing called the Enschedunes Problem, which was one of Hilbert's problems. So this mathematician called David Hilbert came along and he said, well, there's a program of work we should do. This is in the 1920s. Basically, the idea was you got all of mathematics, and he thought, well, maybe we could create this really solid logical foundation for all of mathematics. And we could have a set of axioms, and we could do everything. It was like, just lay it all out. All of mathematics somehow be encompassed in this one project. So he's like, well, therefore, we need to figure out what the formal language would be for that. And then we need to see if we could find a system which has certain properties. So, for example, is it complete? Could everything that's true actually be proved? Is it consistent? Are there no contradictions in this mathematics? And actually, the last one is it decidable, which is there some algorithm to decide whether a mathematical statement is true or false? And so this was just a purely mathematical project.
But you can see the seed of the halting problem for sure.
Yeah, exactly. And Kurt Gödel comes along and comes up with this incompleteness theorem and says it doesn't matter what you try, it's going to be incomplete, which kind of went poof, blew up the whole.
Oh, sorry. Did I just burn your domain
I was just
to the
going to say,
ground?
I thought that Hilbert's problem was one of the unsolved math things.
Yeah. But
that's why.
But you just ruined everything. And then Turing is like, well, I think I'm going to go and think about this whole decidability thing, and I'll go and look at this, and what can we actually decide? And so Church was doing that with the lambda calculus, and Turing with Turing machines, and the equivalent of Gödel's incompleteness theorem is the halting problem. It's like, actually, there's some things you won't be able to decide whether these programs halt or not. So, at this point, David Hilbert's just like, my whole program is gone. Thanks, guys. But what comes out of that, because of this decidability is kind of mechanical, is computers. So I think there was a lot was ripe in the 20s and 30s, and then of course Second World War happened.
Right.
We needed practical machines.
And is this crew aware of Babbage and Lovelace? I mean, are they well enough known that they would have been aware that they had done this work?
So this references a little bit, but they're not building on it. They're off on the side doing mathematics, and they're not really thinking about this machine. It's only later that they sort of, oh yeah, that's kind of similar. That's similar to what we're doing. But it's much later. It's not a linear progression through these things.
Huh. Wow. And so, I don't know, and maybe it's the way you're describing it feels so cinematic. I mean,
I know,
feel
it feels really nice.
There's got to be a movie, right? We got to figure out like who stars as Babbage and who stars as Lovelace. It feels like, I don't know, it feels like there's a great movie to be made here about their story. So, and it must have been amazing too to have all that correspondence between the two of them.
Mm-hmm. Yeah, there's loads of correspondence, Lovelace's letters, and then, her Babbage's letters and Babbage's writing and her writing, and then a bunch of people that they spoke to and described what they were doing. It's very interesting to see it because it gives us a lot of background references. One of my favorite things about Lovelace is that her mother, so Lovelace's father was Lord Byron, who was a poet and quite famous, and also a drug addict and many other things. And Lovelace's mother didn't want her daughter to have this poetical spirit because that was really bad for a girl, right? To have the poetry of her father. And so she made her learn mathematics as an antidote to that.
Mm.
That's how she was taught. And then one of her tutors was De Morgan of De Morgan's
Oh my
Law.
gosh.
Whoa,
Okay.
that is dope. Whoa.
It's like, and De Morgan is here. Like, he's got a cameo.
Yeah, exactly. De Morgan's like, who are we going to get? Who are we going to get to teach Ada mathematics? Well, De Morgan, he'll do. So
He's available.
So she had this very strong mathematical background. And, the only thing about Lady Lovelace, it does come across a little bit in her letters, is she does have quite a high opinion of herself. Hey,
wait a minute. In her defense, it sounds like
If one is going to have a high opinion of themselves,
she's
sounds
like-
like she qualifies.
Yeah, exactly. She's like, I'm kind of acing it over here. Like, I don't know if you're like, do I need to remind you that music can be represented as information? Like, okay, yeah. Well, like, sorry, what have you done again?
Like, I was tripping up to Morgan when I was 12.
Yeah, exactly.
Well, actually, De Morgan did say about her, she really is an original thinker in mathematics and could actually be a first-rate, eminence, I think is what he said. So, and she was very young as well. But incredible story for the two of them. And, they obviously managed to get the poetry out of her, get the mathematics into her. So.
Yeah, that's crazy.
It is just amazing to think about, and to think about all the kind of cast of characters that are around. So in terms of building the analytical engine, what's the progress on that? Because I think that and to kind of give you some of the context for the question too, one of the things that's been so fun about doing this podcast is talking to people about how they got into computing. And we learned about this thing called Dr. Nim, and this mechanical manifestation of Dr. Nim that Ron Minnick described as being really inspirational to him. And based on that, there's this thing called Turing Tumble that's out there today, which is really neat. And there's something that's really great and approachable about these systems for mechanical computation, because it's so visceral in a way that a smartphone is not approachable in any kind of the same way, and in terms of introducing kids and people to computing. So what's the progress on the analytical engine? Because has that yet been built?
No, goodness me, no. So I created a little charity in the UK to try and get this thing together, and I found basically the two other giant Babbage nerds in the world. So Don Swade, who actually was the person at the Science Museum who ran the project to build the difference engine.
Oh, wow.
And a guy in the US called Tim Robinson, who has been building bits of the analytical engine out of Meccano. And the two of them have been poring over every page of Babbage's notes about the analytical engine. And we now have a massive cross-reference where we can look up anything about this. And so the reason that's important is that Babbage kept changing his mind about stuff. So for example, he's like, oh yeah, we'll use base 10 for this machine. No, let's use binary. No, let's use base 12. No, let's use base 16.
So I was going to ask about the base, because the 10 is effectively arbitrary.
Yes.
And you're presumably looking for something that has the best mechanical properties.
Right. That's why
And so it sounds like there was some vacillation on that.
Yes, there was. So his decision was base 10 because it's easy for the UI, right? A human can inspect the state of the machine and know what's going on. It makes it easy. It makes the mechanics of the machine more complicated for addition. And one of the reasons why he wanted to have binary was it make an adder really simple, right? But he realized that if he had binary, then his memory locations, right, his bytes, which are literally stacks of gears, would be so tall mechanically you'd have difficulty moving them.
So how much memory does he have in the analytical engine?
It depends which version you're talking about.
Right, yeah, right. Which base? Yeah.
Somewhere between 10 and 1,000 memory locations, each one being, depends on the spec exactly, but typically a 30-digit, base 10 number.
Wow.
That's cool.
That is cool, but it's also, that is small.
But guess what?
That is really small.
I might need double precision. I'll invent a system where I can link two memory locations together. So if I need 60 digits, I'll be fine.
That's crazy.
So yeah, the quad word, the mechanical quad word.
Yes. Yeah.
Wow. Okay. So
that's crazy.
So you're trying to. So there's efforts. You got to figure out like which version of the analytical engine are we building here.
Exactly. So the next step right now is, now that we have all this stuff together, is actually to take some of the hardware description language, the Verilog of the 1800s, and try to figure out, okay, which bits are missing. Do we have enough to actually create something?
Has it been built in simulation?
No, not yet. Not yet, because there's literally 10 different written plans, and there's thousands of pages of, I'll try this out. I'll try here's like a little sketch of some cogs, and maybe it'll work like this. And here's the microcode. And by the way, here's a program I produced on paper. It's a massive archaeological thing. Whereas the difference engine, before Babbage's death, he left behind a complete set of plans. So that it was the simple task, the mere task of interpreting those plans.
Right.
Yeah. This is much more archaeology on what he was doing.
Yeah, I was gonna ask because I stalk these weird auctions online, and I saw there's some letters and stuff from Babbage and Lovelace in a random auction. So it's how do you collect all these things when it seems like they're almost also scattered across the world?
Well, the good thing is his actual papers he arranged through his son. They would be donated to the Science Museum in London. So the Science Museum has kept them since the 1800s and preserved them and then scanned them. So there's a lot. So the definitive stuff is there. The letters are more interesting just from the historical context of what were they thinking and who were they interacting with.
Jess, Tim Robinson maintains the difference engine #2 at the Computer History Museum in Mountain View.
What?
That's right. Yes.
Oh,
responsible for operation and presentation of it. So nice. we're heading there in a couple of weeks, John.
Yeah, he knew how. Yeah, he's run it. Really knows how it works. So between Tim and Doran, they've been going back and forth on what are we going to build and what does it look like. But the cross-referencing was massive. It meant transcribing thousands and thousands of pages. And you're talking about handwritten in Babbage's lab notebook, copperplate writing, which even just staring at one of them, you're trying to interpret what he's saying.
Oh, right. Yeah, I mean, to just imagine there's a lot to be done, but it feels like this is an important thing for humanity to do, don't you think?
Well, I know the computer nerds think that, but I'm not sure humanity thinks that. So I know that I think it's really, really cool, and I'd like to see the machine. What I hope is that we can build a machine eventually that, were Babbage to appear in the room, he would first of all look at it and recognize his machine, and then in his typical curmudgeonly way say, why the hell did you build this version? The next version is going to be
much better.
Right. Well, you would wonder what he would feel, because then, I mean, all of these things got so improved upon in the machine. Now he's like, why are you building this at all? You've already built this machine.
I know. He probably would just berate us for being idiots.
Right. You have these computers in your pocket. Why are you building this mechanical thing? But it just feels like it would be valuable to go. I mean, it's so important historically, you would think. And you gotta think one of these billionaires can actually back up the truck. I mean, they spend money on so much dumb stuff.
Sand Hill Road should fund it.
Right. Oh, you mean all these super yachts and all this other garbage? Yeah, Sand Hill Road.
That's fundable.
I'm not sure that's fundable. Speaking as ones who have started a computer company, I don't know that it would make our pitch any easier.
Now, if that helps people play tic-tac-toe on a social network, that's fundable.
Yeah, exactly.
I mean, and who doesn't need a locomotive-sized mechanical?
All right, so that's a good question. Do we know even what the physical size of a completed analytical engine would be on the order of? Sounds like
Yeah.
locomotive
We do.
size.
Yeah,
Whoa.
like a small steam locomotive.
That's
Wow.
cool. That's dope.
Yeah, I think
That's
it'd be
feasible.
great. I think it'd be fantastic. I mean, very, very slow. We know that. Well, we have some idea of how fast it would run. It takes, so roughly based on the data we have, to fetch 2 numbers from memory and put it into the CPU for addition takes 3 seconds.
Whoa.
But that's why he invented pipelining, because then he's like, hey, while it's adding, I can get the next 2 numbers and put them on the input bus. So
Yeah. Wow. That is slow. So you
Yeah.
do wonder, would that have been prohibitively slow? I mean, would it have been able to do things that were otherwise, surely.
Not his next version.
That's right. Exactly.
Exactly.
Right.
Why you built that one?
Right.
I got one to do it in 1 second.
Amazing.
The other thing that's quite interesting in his stuff is he essentially has the whole RISC versus CISC
What?
debate in his head, because he's like, well, I can make a simpler machine if I have simple instructions.
Interesting.
But if I make complex instructions, then the machine will be faster because I can do something like, square root operation or something. So he's like trying to decide, he's trying to play off, what do I build versus what, the performance of the machine.
And does he have any inkling of the stored program computer? Does he think about putting these instructions in the memory itself?
No.
Interesting.
He's not. That's a great question. He does not think about that at all. They're all on the punch cards, and there's definitely no sense that you could put the program in memory. He obviously has a sense of looping and things because he's going to need it.
Right.
So he
Right.
has as a program. The other thing that's really wild is that there's an operator for this computer, and the operator's job is to do what the analytical engine tells that operator to do.
Fun job.
Yeah, same job, right? So he envisaged there being a wooden cabinet full of programs, and essentially subroutines. And at some point, the machine rings a bell, which is handled by one of the punch cards, and says, "You need to load up, the cosine subroutine right now. So I need to do it because I haven't necessarily got it all. Because there's a limit on. He thinks there's a limit on the number of punch cards you can have in a reel. There's going to be some physical limit. So the operator has to come over and either feed in new instructions or new data to the machine. But no, he does not think about it as a stored program at all.
That is interesting. So, I mean, because I've always called this John von Neumann's gift, and it sounds like I can still call it John von Neumann's gift. It sounds like it is not John von Neumann's gift as stolen from Ada Lovelace and Charles Babbage.
Yeah, I mean, I think so. I mean, to a certain extent, the Turing A machine,
Right? Yeah.
being a universal machine that reads a program from the tape, is the same kind of thing. But yeah, Babbage did. I mean, his memory was so slow, and I think he liked the idea of punch cards. So that was where the program was.
Just like the physical idea of punch cards.
Yeah, I mean, go see them in the Science Museum. There's a stack of them standing there with a program on them.
Wow.
I find it so incredibly upsetting. Every time I look at that stack of cards, I'm like, there's a program trying to be run right there. It's waiting.
Yeah,
It's
it
waiting
is.
150 years, and no one's running it. So, I mean, you can
No,
run
that's so
simulators
messed
of it.
up.
Well, it feels like you at least want to be able to do it in simulation,
Yeah.
not actually machining the thing, but actually being able to simulate a completed thing.
Absolutely, and we'll get there, right? That's the sort of the next thing. Once you say, okay, this is the machine. Okay, now we can simulate it. We can simulate stuff.
That's cool.
And it's interesting actually when they built the difference engine, because they were doing it in the mid 80s, they couldn't do a simulation because simulation software wasn't
Right.
good enough on the computers we had at the time. But now, actually, yeah, we can simulate the whole machine physically, right? Do physics simulation of it. So
Whoa, that's cool.
Yeah, which I think it would be. I mean, I think that would be really valuable. I think that obviously make it easier to machine and debug and so on. But
yeah, absolutely, and we will. The thing is, it's very easy to design a mechanical computer, right? Because we can just go backwards and we can just be like, oh yeah, well, we know all about computing. Let's design a thing online. We want to actually build the thing he wanted to build, not some fantasy version of what he wanted to build.
Right.
That's what makes it a slow.
right, because what he wanted to build is so ill-defined.
Yes.
Yeah, that's right. All right, we got to take another quick break, and we'll be back with more John Graham-Cumming on the Metal.
On the Metal is brought to you by the Oxide Computer Company.
Take it from Paul Guaz. Just go to oxide.computer and let's please get back to the show. All right, we're back. And Steve, I think you had a question for John.
Well, yeah, I want to ask about another fascinating person in computer history, Douglas Engelbart, that you mentioned in a 2013 OSCON talk when you were talking about how a lot of the innovation of today are maybe recycled is too strong, but had been imagined and had been built before. But you talked specifically about him and what was called the mother of all demos.
Mother of all demos, yeah.
I wanted to ask a little bit more about that.
Yeah, I mean, the thing that's fascinating about computing, and I can't ever quite reconcile this in my head, is that we both forget about what the past was and think everything is new. And we benefit from that and lose from it because we sort of reinvent stuff. And it almost seems like somehow it's necessary to reinvent stuff, that if we were stuck in the past, we never would invent new stuff. So there's this weird thing where it's like, you look at stuff that gets invented today and the cloud computing and VMs and stuff, and you're like, wait a minute, wasn't a lot of this done in mainframes? But it's almost like it got forgotten or hidden away or looked down on. And I find it really weird. And the mother of all demos is fascinating because, you're talking about forever ago, and here's a guy doing desktop video conferencing, and he's got hypertext, and he's just interacting with the computer over, a phone line. It's a little bit more complicated than that, but it's just fascinating to see. And then, inventing the mouse because, hey, we need to have the mouse because we need some pointing device. And that for me is really, really interesting. But it's hard to reconcile with, we in some ways seem to like to forget the history of computing and reinvent things.
Well, so is it reinvention, or 'cause to me, I think that the present and rhymes with the past? Because you look at, take cloud computing and virtualization and so on, there are certainly very, very important elements done very early in computing, but modern virtualization actually did have to solve a bunch of problems that had not been previously solved. My view has always been that you want to really look to the past to make sure you understand what has been done before, so you're not resolving the same problem. But I think sometimes we overly lionize the past and we think that every problem has been solved. I don't know.
No, I think that's true. I mean, it's certainly the case that every problem hasn't been solved. Although I think it's interesting as, the amount of theoretical work that was done in universities. If you go back and look at, Lamport clocks and all this kind of stuff, where it's all distributed computing stuff being done before we really had enough distributed computing to worry about that.
Yeah.
I find that fascinating.
Yeah.
There was all this work. And then, Google comes along and builds massive things. And it's like, oh yeah, we can actually go back and look at all this research that was done. So I think people do need to look at the history, but also be kind of free to say, yeah, we can do this because now we have fast enough processors, or enough processors, or good enough networks, and all those kinds.
Yeah, when also making it more robust. Because I remember, being very trolled by an Alan Kay interview where he was lionizing how Unix was perfect in the 70s, and we how is it that we had a Unix kernel, a complete Unix system with 10,000 lines of code, and and I'm thinking bud, I've been in that code, and yeah, there was. It's very important work. I don't want to denigrate it, but there were also all sorts of conditions that it simply did not handle. Mm-hmm. And it would toss under if you ran out of processes, the machine would panic, it's like,
yeah.
So let's take it easy here in terms of not everything that's been done since then is, so I don't know. I'm always of mixed opinion.
I agree with you. We've made all this stuff work to the point at which, we've managed to give the general public supercomputers in their pockets, and those machines seem to work somehow, and they don't have to worry about, inodes running out or any nonsense like that. We've made stuff pretty reliable. I agree with you. I think it's difficult, right? If you see the perfection of the idea in Unix, but the implementation isn't quite there, it's easy as a program to be like, well, that's just an implementation detail.
Right, exactly.
We'll get there. But the real step was the structure of the system, or the decision that everything's a file, or whatever was the decision. So I think that's easy. But yeah, making stuff actually work in the real world, it's really hard. Really hard.
And so actually what I really like as a technology that is very aware of the past but still very forward looking is RISC-V. I don't know how much you've gone into the kind of the innards of RISC-V, but I just love the way they have so deliberately learned from everything.
Yes, I agree. That's a fascinating project. It's one of those things that I probably wish I had more time to spend messing around with. But yeah, agreed.
What I just love, they got these tables of all these mistakes that various architectures have made, because it's and it's all of these historic RISC architectures have got these weird warts, and they've kind of gone through and systematically eliminated them, at least in the instruction set architectures.
I don't think people give enough credit to past history when they build things.
Right.
Honestly.
Well, and I think RISC-V is a model in that regard, where it's like, hey, we paid attention to the past, but we're not going to be confined by it.
We're going to do that. Yeah. Yeah. That's a good way to look at it. Definitely.
So not to fixate too much on the mother of all demos, but I was curious, was it actually a demo?
Yeah.
And who was it a demo to?
Yeah.
And it's recorded. It's recorded on video.
Okay. So he just recorded it on video.
No, it was done live. So it was done live in San Francisco, I think.
Right. But I mean, so when it says it was recorded on video, I mean, we have a video of the demo.
Yes, we do. We do. It's 90, I think it's like an hour and a half, something like that, 90 minutes.
Cool.
And there's everything there. The mouse is there, video conferencing, real-time editing, collaborative real-time editing with somebody else who's remote.
And what was the reaction at the time to all this groundbreaking technology?
I think my understanding is that everyone was completely blown away because it was, it was networked and it was all this technology was actually happening. And, it's 1968.
Right. So this is before Park, right?
That's nuts.
And the mother of all demos inspires a lot in Park, and Park in turn inspires a bunch of the industry.
That's
Yeah,
cool.
this is SRI. It was done, right? And I think, I don't remember where it was done. It was somewhere in San Francisco. The
Yeah, it was in San Francisco, I believe.
And did this just shock everyone? I mean, were there teasers that this was coming? Did people know what he was working on?
But, it's like, who was it that said, what's the quote? Like, the future is here, it's just well hidden. Whatever. What's the...
Oh, no, it's not evenly distributed.
That's it. That's right. It is.
Yeah.
And who is that? That's a...
It's William Gibson.
Right. Thank you.
Yeah.
And I kind of feel the same way about folks that were kind of in the know knew about that. But it's just like, when we were talking about Tom Lyon was here, who would describe going up to Park where his brother worked. And there was a time in Silicon Valley when
one of his brothers, one of his
5 million
illustrious,
prolific brothers, you would walk into Park and it was like walking into the future. And a lot of people describe that.
That's cool.
But it was, it was all still, it was in the present. I don't know what the analog is for today, though. What is the
quantum? Those people would claim that they were the future. I'm just saying. I'm not defending it, but
maybe it is.
Well, probably, yeah. Although my understanding is at the time, some people thought that Engelbart was a bit crazy until he did the demo.
Oh, interesting.
He had all these ideas that all this interactive stuff was going to happen, and
just too wacky.
It was just too wacky and out there, and it's like, drop the mic, basically. It's like, by the way, boom.
Right, because any one of those things would be groundbreaking to a certain extent.
Absolutely.
And he's like, oh, no, wait, there's more.
Yeah, exactly. It's like, by the way, we're doing hypertext. Now we're going to switch windows. Now we're going to do a video conference. I'll just show, and then we'll do real-time editing.
And then I have to believe there's people that were like, oh, this demo's rigged. Does this actually work?
Yeah, and it did actually work, although it was hell getting it working. I remember reading a thing about it must have been going to probably, Bell and asking to get the phone line, the data connectivity between the two locations working. I think they had to use microwaves, actually.
Oh, wow.
That's cool.
But I mean, it was totally crazy because it was Menlo Park to San Francisco, if I remember well.
Whoa.
That is amazing. Is there a book on the mother of all demos just on that?
No, there should be.
There really should be. Yeah, it's kind of amazing that there isn't. I mean, it's certainly referred to a lot by the Park folks.
But you could just watch the videos on YouTube. If you've got an hour and a half, to watch a black and white video of somebody making a shopping list and editing, online.
That's cool.
Crazy.
It is amazing. And in 1968, it's just stunning. Yeah, and it's like, where is that? Where's that demo equivalent today? Yeah, I don't know if it's quantum or not.
Well, maybe what's this crazy thing Elon Musk is doing, drilling holes in people's heads?
Oh, yeah.
Wait, what?
Fair enough.
Hold on.
Hello, he has a new company.
The holes in heads?
Yeah.
It's like
cerebral implants
into your head and connects you to it or something.
It's like you're racking up your brain to the cloud.
Yeah, they're doing POCs right now.
Oh my God! Yeah, you first. Yeah, what? I don't even know. Words fail. Come on. I mean, it's just. This is why I think maybe when you get these things that feel very like a big leap, sometimes it is hard to differentiate those from the things that are leaps that don't actually amount to anything. Like the whole nanotechnology. There was a period when nanotechnology was absolutely going to be the future. and K. Eric Drexler and the gray goo. And I mean, John, you remember all this whole era?
Yes, I do. And I remember being utterly fascinated by nanotechnology. And then Neil Stephenson wrote The Diamond Age and made it seem like it was all coming. And it was, yes, I really wanted, you know what I really wanted? I wanted nanobot shaving cream. I wanted to be able to rub tiny robots on my face and have them shave me.
That's terrifying and captivating.
Oh my God. Well, no, and this is the whole, so the nanobot shaving cream, Mike, that's unique to you. I don't think I heard that.
That's my thing. That's my thing.
That's your thing. But the whole, no, this whole nanobot idea. This is Feynman's idea of the bot that builds the smaller bot. And there was an era in the, I would say, late 80s, 90s, when this was a very captivating idea. And then you kind of realized that, like, you know what, this is not coming.
I wrote this book, right? Drexler wrote this book called Engines of Creation. It was about these machines that make machines. And there was going to be this thing called the gray goo, which was like the gray goo, right? Over the whole world. By making copies of themselves.
Well, no, but and he would give this very captivating talk about like your demo, and he would talk to especially folks in the military industrial complex about, you know, a cow is a machine that turns grass into steak.
Yeah.
So based on that, like, why is it not possible for me to turn you into gray goo? And
what?
So the idea is
that doesn't line up though. Like,
well, you know, the admirals and the generals, they got very excited.
A lot of head nodding.
Yeah, a lot of head nodding.
Yes, it was the 80s.
It did. No, there was some truth to it, and I feel that like. And nanotechnology, I don't know, John, when did you have the conclusion that, like, I need to stop waiting for this, it's not coming? I mean, I think actually...
Yeah, I don't know. There's a lot of things I'm waiting for. I've stopped waiting for. I've stopped waiting for domestic robots that are of any use, and I've stopped waiting for flying cars and jetpacks, and, you know, the gray goo was along the way, I guess.
Yeah.
But the big problem with it, I remember being fascinated by it, and then just the thing about, you know, the Drexler thing was it'll all be done by having just you have a whole load of chemicals and we'll just assemble stuff out of chemicals. And it's like, well, chemistry is actually really hard. And you can't just like link atoms together to make plastic. You know, it just doesn't work like that. So I think it was around then I was like, this isn't going to happen.
Yeah. And so for me too, it was on when I read Engines of Creation and realizing, well, first of all, this is probably an overgeneralization, but I do feel that people that want to go by first initial name, there's there's something there. There is it's like it's K. Eric Drexler, J. Edgar Hoover. There's E. Howard Hunt. There are a bunch of ones that are anyway. Whatever.
This is like the theory about serial killers, right? They're all having names like that. They would have two names.
Whoa.
Right? Yeah, exactly.
That's fair.
Yeah. So so there's something weird about that. But honestly, and this is an interesting contrast to Babbage, because also Babbage had not actually built anything, and yet what he was onto was very legit. Yeah. K. Eric Drexler never built anything. There was nothing. There was no demonstrable system at all demonstrating any of these ideas. It was all ideas. I mean, and when I realized that, I'm like, wait a minute. There's nothing. It's not like we can't point to anything that is getting towards what we would call a nano machine. There's not a micro machine. There's not a milli machine, let alone a nano machine.
And then, what did we get out of it? We got out of it like 3D printers. Which are fun, but yeah.
Yeah, exactly. I got to ask you this, because I definitely wonder if, we've got the first snowflakes of the next AI winter are surely blowing.
I'm not a deep enough expert in this, but it sure feels like it.
Yeah, and please, the lack of expertise has never prevented me from shooting my mouth off, so please do not let it prevent you from, but I do wonder if AGI is going to be this generation's equivalent of moon bases and flying cars, where you're going to have, when the Gen Zers, when they grow up, they're going to be like, yeah, the artificial general intelligence that I was promised when I was a teenager never arrived. I definitely wonder about that.
I was promised that too, right? The first AI winter, I thought there was going to be, expert systems. That was the thing. We're going to get so good that they'd replace doctors.
That's right.
All this kind of stuff was going to happen. And then I was like, yeah, no, No, that didn't happen.
It is. So it's actually funny that you should mention it about medicine, because that's exactly what my father was actually doing, was working with another physician in San Diego who was using expert systems on medicine. And it was interesting what there's a lot of value, but they were very limited in terms of what they would ultimately able to do.
Right. Well, and then, when IBM has pushed very hard the idea that Watson is going to identify cancer and stuff, right? So it's the same stuff again.
So I want to float past an idea for you. I believe that that we in computing, to prevent the further seasonal cycles in AI is hereby ordered to change its name to automated pattern recognition. It may continue to exist as a discipline, but it must change its name because its very name is leading to this seasonality.
I see. They're overselling it, basically.
They have to oversell it because it's in the name.
Yeah. I also, I think that flying cars are not exactly dead, by the way, because you said this twice now, and with electric VTOL and the flying taxis, if that works out, although it probably won't.
Okay.
Maybe. Maybe.
I'm just saying.
I mean, honestly, growing up, I was definitely promised flying cars, protein pills to eat everything, all this domestic robots.
Yeah.
And literally the future has turned out to be trying to keep all my batteries charged. Great. It's like, great. That's what I got. I need to charge stuff up.
There's inventors to all that just saying it's just implementation details.
It is just implementation.
We're almost there.
We're almost there. Yeah.
Yeah, but I think just that because I grew up in the past that John did, where we were really promised flying cars,
like the Jetsons.
Yeah. The Jetsons, it's actually, if you really want to capture the zeitgeist, it is that final scene in Back to the Future.
Back to the Future, I was going to say, yeah.
Right.
That is what captures that 80s zeitgeist of what the future was
going
to be.
That's very different than the electric VTOL stuff.
Yes.
Because it's basically a helicopter.
Also moon bases. Frankly, I was promised moon bases.
Yes. I was promised moon bases, and
it's now Mars bases.
And
it's fine.
And I built them with Legos.
Mars bases are coming.
Mars bases are,
3 flights a day. Just sit tight.
Yeah, is that for people who've had their skulls, had holes drilled in their skulls?
Exactly. Your Tesla is going to drill into your skull and fly you to Mars.
It's going to be a lot of latency back to Earth.
All right, well, with that dystopian view of the future, John, thank you so much. This has been
so much fun.
This has been so much fun, and such an interesting tour through the history of computing.
Thanks very much. Lovely chatting with you. Good luck with the company.
Thank you. Thanks.
All right.
You've been listening to On the Metal, Tales from the Hardware Software Interface. For show notes, to learn more about our guests, or to sign up for our mailing list, visit us at onthemetal.fm. On the Metal is a production of Oxide Computer Company and is recorded in the Oxide Garage in Oakland, California. To learn more about Oxide, visit us at oxide.computer. On the Metal is hosted by me, Bryan Cantrill, along with Jess Frazelle, and we are frequently joined by our boss, Steve Tuck. Our original and awesome theme music is by JJ Wiesler at Pollen Music Group. You can learn more about JJ and Pollen at pollenmusicgroup.com. We are edited and produced by Chris Hill and his crew at HumblePod. From Jess, from Steve, from me, and from all of us at Oxide Computer Company, thanks for listening to On the Metal.